is going to include the bar rotating with forces on it. You have to find the net force, and then you also have to find the angular acceleration, moment of inertia, and you have to report to me the angular velocity or the angular displacement after a certain amount of time. I showed all that last time. I'll show you some examples. Also, you're going to have a conservation of angular momentum problem. We have two spinning objects come together, and I ask you, well, what is their final angular velocity? You're going to have a manometer problem, which we worked a couple of those, where I'm asking you to tell me the unknown pressure, and also asking you to tell me which pressure is greater. You have to know that anyway to find the unknown pressure. And then you're going to have a problem like this. This is number 4 in the homework. I think we've done one like this, but we're doing it now. So you're going to have two things that I'll ask you. First of all, I'm going to give you a picture. In this case, it's going from 10 to 2.5 square centimeters. So in this case, the pipe gets narrower, and I will give you a picture that'll show that. It'll either get narrower or wider. And so this area here, I'll call this A1. It is equal to 10 centimeters squared. And this area right here, I'll call it A2, is equal to 2.5 centimeters squared. And then I tell you that the velocity here, V1, is 275 centimeters per second. So the first thing I want you to do, and that you'll need to do on the exam, is to tell me what is the speed of the fluid in this pipe. That'll be the first question, or there'll be two questions. In order to do that, I just say that A1 V1 is equal to A2 V2. And then I can put in my values. Although, look, my area goes down by a factor of 4, so I know that my velocity has to go up by a factor of 4. So I could just say, well, it's 275 times 4. But we'll just do the equation of how that works out. So 10 times 275 is equal to 2.5 times V2. And I find that V2 is equal to 1,100 centimeters per second. Or I could report that as 1.1 meters per second. I will use SI units. I don't know why I did the centimeters here. So that's the speed. I'll ask you to find the speed in that second section of pipe. We've done that a number of times. I don't know that we've done this part. I've shown you sort of how it works, but I don't know that we actually crunched the numbers. The second thing that I'll ask you to do is to tell me what is P2. What is the pressure in the second section of pipe? Now I do tell you P1. P1 is 1.2 times 10 to the 5th pascals. That, by the way, would be 1.2 atmospheres. But if a pressure is ever given in atmospheres, then you have to convert it into pascals. Pascals is the SI unit. So, for example, if I said P1 is equal to 1.2 atmospheres, I would have to then convert that and say that it's 1.2 times 10 to the 5th pascals. I don't think I did that on the free response, but I might have. I'm not sure. I don't remember. But you definitely need to know how to convert between atmospheres to pascals, and that pascals is the SI unit. Okay? So in order to find P2, what we do is we use Bernoulli's principle. Recall that Bernoulli's principle is this big old long equation. It had 3 terms on each side. I'm going to leave off the rho GH term. Remember how we talked about how the height of the fluid will always stay the same, so it's not going to change its potential energy. So I'll just leave that off, and I get an equation that looks like this: 1/2 rho V1 squared plus P1 is equal to 1/2 rho V2 squared plus P2. And I want to solve for P2. I'll go ahead and put in my values here. 1/2 of rho. Rho is given here 1.65 grams per cubic centimeter. That's 1650 kilograms per cubic meter. That's what your table gives, by the way. Your table gives the density in SI units. The SI unit is kilograms per cubic meter. V1 is 275 centimeters per second. That's 2.75 meters per second squared, plus P1, which is 1.2 times 10 to the 5th pascals. And then that's equal to 1/2 of 1650 times 1.1 That's my new speed that I found, plus P2. Okay? I know that because the speed went up, that the pressure has to go down. I'll leave y'all to crunch those numbers. I just have to figure out what this whole thing is to subtract this. But I know that my P2 definitely has to be less than 1.2 times 10 to the fifth. Okay, so that'll be the second part. If you're doing your calculator, just beware that if you just give me a number and I don't see anything written down and it's wrong, it's going to be off. Okay, so I need to see your work. If you write the equation, if you just make a funny little thing, use it. All right. Now clear on the free response. We can look at some if y'all want. Y'all want to work through some of the free response? Or y'all have any specific questions you want to look at? No? Okay. Look, we haven't done all the concept tests. I just want to sort of skim through it. We're not going to answer them all because I think some of them we've already talked about. We have done all these, and I posted it on Moodle. I mean, on Canvas, excuse me, and I just sort of want to go through some of these. They have explanations, so I'll leave you to sort of go through them. I recommend that you print them out and maybe print 6 slides to a page, or just use them on your phone and use them as slides, and just use them sort of as, I don't know, as a study guide. Let's see. I just want to hit some of the ones that are more difficult. Okay, so here's one that students often miss. I'm not saying this is on the exam, but I had put it on the exam before. I have a boat carrying a large chunk of steel. It's floating on a lake. The chunk is then thrown overboard and sinks. I wonder what happens to the water level in the lake. Often people think that the water level rises. We're not going to do it as quick a question, I'm just going to, but that's not really what happens. Really, the answer here is that it drops, and this is the reason. Imagine this is my lake, and here's my boat, and I have this steel in it. All right, so the steel is sitting in the boat, and the amount of fluid that the boat is displacing is equal to the weight of the steel. That is, the weight of the steel is equal to the weight of the displaced fluid. So because steel is more dense than water, that volume of water that has a weight equal to the steel is bigger than the volume of the steel. Right? You have the steel, then you have the water that has a weight equal to the steel, but that water just occupies more space because it has a density that is less than that of steel. Then if you take this out, now the steel sits on the bottom of the lake. The water level will rise because now the only amount of water that it's displacing is equal to the volume of the steel, the volume of the steel block. Right? No longer does it have enough buoyant force to hold it up because it's not displacing enough water to provide a buoyant force that would buoy it up to the top. Okay, so in this case, the water level would go down because when you put the chunk of steel in the lake, that it displaces actually less volume than it did when it was in the boat. When it was in the boat, it displaced a lot of volume. But when it's just sitting on the bottom of the lake, it doesn't displace as much volume. There's some similar questions that sort of explore that. There's a picture. That's right. When it's in the boat, it displaces more water because you have a buoyant force that's equal to the weight of the steel. But remember, the buoyant force is equal to the weight of the displaced fluid. And so the displaced fluid has a volume, has a mass or a weight equal to the weight of the steel. But the volume of the water is bigger than the volume of the steel. Okay, we'll look at this. There are different questions that look at the same idea. So here I have 2 scales. One of them has a beaker that's completely full of water, and then the other has a wooden block that's placed into the beaker. Right, so I place this beaker. Some of the water, by the way, will run over. Right, you put this wooden block into the beaker, and some of that water will overflow from the beaker. And now I want to know which one of these reads the larger weight. And so a similar idea here, as we saw in the previous one, that the buoyant force that's acting on this block is equal to the weight of the block. But also, the buoyant force is equal to the weight of the displaced fluid. And where did the displaced fluid go? It flowed over, right? So you lost that fluid, that water, that the block displaced, and it is the weight of that displaced fluid that is the buoyant force, which is also equal to the weight of the block. So in this case, the water, we lost enough water to equal to the weight of the block. So these two scales, which one would read the larger weight? They would both be the same. Right. So 3 is the right answer, C is the right answer here. Okay, these are some flow problems. We talked about this in class, that the pressure actually decreases. Okay, so the blood pressure, it matters where you measure your blood pressure. You would measure on the arm, but if you measure your blood pressure on your ankle, you'll actually get a higher blood pressure because you have like all this fluid in your body that is sitting on top of your ankle, and so it adds that additional pressure because it's lower. If you have this column of fluid basically in your body that rests on top of your feet. That's why your feet, if I don't for y'all, but for some people your feet get swollen as you get older because you just have this difference in the fluid sort of settles into the lower parts of your body. That's why too, if you ever done a headstand, all right, what happens to your head if you do a headstand? It turns really red, right? Because all your blood flows there and it feels like your head's about to explode. So, all right, so the blood pressure will be higher there. If you have a chimney and there's a wind blowing outside, this is like Bernoulli's principle that your smoke rises, but if I have a wind blowing outside, then that causes a low pressure, and that creates this, that the smoke is actually pulled out. It's just like the ping pong ball, it's pulled out of the chimney. Okay, those are sort of the hard ones. You'll take a look at those, though. If you have questions about them, let me know over the weekend. Email me or you can text me, it's fine. Let's look at some of the past exams. We'll start with the one in the back of your book. So, I don't think there are any of these questions on any past exams 3. So just beware. Oh, I don't have any fluid questions on this. Let's do the, so we'll go to some of the other exams. Let's, have a question like number 2 as one of your free response. It'll be very similar to this, except though your free response will have a bar, not a disk, but it'll work out exactly the same. So in this case, you have to do several things. First, I'd ask you to find the net torque. And to find the net torque, I would say that this is torque 1, this is torque 2. Realize that this one is causing a clockwise rotation. Torque 1 is causing a clockwise. Torque 2 is causing a counterclockwise, so it's positive. So the sum of the torques is going to be negative torque 1 plus torque 2. It's going to be negative 10 uh, 10 times 2 times sine of 30 plus 10 times 2. So that gives me a net torque of 10 Newton meters. And because it's positive, that is a counterclockwise torque. Right, that's the first question I'll ask you. I think it actually is number 1 on the test. The second thing that I'll ask you is what is the, it's not energy, I'll ask you what is omega or theta after, we'll do 3 seconds. Okay? So in order to do that, you have to do several things. First, what is the moment of inertia? In this case, it's a disk, so that's 1/2 mr squared. In your case, it'll be a bar, so that's 1/12 mv squared. That's on your equation sheet. So that's 1/2 of the mass, which is 4 kilograms, times the radius, which is 2 squared. That's 2 times 4, that's 8 kilogram meters squared. Next thing that you want to do, that's first thing. Next thing is to find out what is alpha. That's the angular acceleration. That's torque over I. That's 10 over 8. 5 over 4, so that's 1.25 radians per second squared. And then the final thing that you'll need to do is tell me what is omega or alpha. Well, let's just do omega. So we'll say that omega is equal to alpha times t. That's 1.25 times 3 seconds. That's 3.8 radians per second. Or if you were finding theta, then you would say theta is 1/2 alpha t squared. So I'm going to count out equations with the half percent. People have their equations. If you have the full equation, it would be a separate page to compare it all. Yeah, so in that question, which I gave them, you're not going to have the same thing, though there will be multiple choice questions where you have to find the rotational energy. In this case, that's what I'd ask. So yeah, you do 1/2 I omega squared, which based in this case, you have to find omega and then find energy. Okay? All right. The second one that you'll have will be an angular momentum problem. Let's see if this one is like that. Yeah, something like this, like number 3, something very similar to this, where I have a bar that's rotating. It engages, in this case, with a stationary flywheel, and then they both spin at the same rate. By the way, these two questions, or no, this question will be on your final exam. I am going to tell you what's going to be on your final exam. Am I going to tell you right now? Yeah. You're going to have a projectile motion problem. That's for exam 2. You're going to have an inclined plane. That's also for exam 2. And then for exam 4, you're going to have this problem and a manometer problem. So an angular momentum problem and the manometer. Oh, wait. Yeah, manometer problem. Okay? I'll tell you all that again later as we get closer to that final. But if you're beginning to think about the final exam, that's what you got. Exam 2, inclined plane, projectile motion. Exam 4, manometer and angular momentum, like this one. So here on this one, we say that Li is equal to Lf. The initial angular momentum is just the angular momentum of the bar, because the disk is not spinning. And then the final angular momentum is the combined angular momentum of the bar plus the disk. I'm going to go and find the moment of inertia of the bar. That's 1/12 mb squared, 3 times 2 squared. That's 1. And then the moment of inertia of the disk, which is a cylinder, is 1/2 mr squared. 1/2 of 4 times 2 squared. Oh, there should be a squared there. That's 2 times 4, that's 8. So this is going to be I of the bar, omega initial. This will be equal to I of the bar plus I of the disk times omega final. So that is 1 times omega initial is 3 radians per second is equal to 1 plus 8 times omega final. So 3 equals 9 omega F. So omega F equals 1/3. 3/9 or 1/3 radian per second. Okay. I think in your exam, I actually asked what is the total angular momentum of the system, and then this is the second part. But for the total angular momentum, well, the total angular momentum would just be this. So for part A, I'll ask what is the total angular momentum? And L is just equal to I times omega. In this case, I know the initial angular velocity, so I just say that it's equal to 3 kilogram meters squared per second. So the first part is asked, what is the total angular momentum? And then the second part is asked, what is the final angular velocity? All right? Take it back. I could ask either what is the final or the initial angular velocity. You would work it the same way. It's just, it would be a matter of, do I know this value or do I know this value? I don't remember which I did, but I could have done either. All righty? And then the third one, or excuse me, the fourth question, that's 1, 2, 3. The fourth question is going to be a manometer question. Let me pull up another old exam, past exam. We've worked through these. This question will also be on your final. You seem unconcerned about this. Are you unconcerned? Or are you just still reeling from organic? Still recovering? Or just afraid of next week? Which is it? Unconcerned or afraid? Afraid. Don't be afraid of this one. It's not a terribly difficult exam, but of course, as you know, if you don't know how to do it, you just don't know how to do it. So, let's see. Oh, by the way, so this is an example of your free response. This one, number 24 on spring night or fall 19, number 24 on fall 19. But that's an example of your free response with the fluid flow. Okay, I don't see one right off, but this is a good example. So this is like your free response. I want to know, I'll ask you two questions. I'll ask you first, which pressure is bigger? In this case, which is it, P or P naught is bigger? P. P is bigger because the level on this side is lower. And by the way, here, this is my known pressure, but I can switch them up. It doesn't matter. Like in the past, I've done, this is my known pressure. You know, your known pressure is P naught. So since P is equal to P naught plus or minus rho GH, and since P is bigger, that means that I'm going to be using a positive here. P is bigger than P naught, so that has to be positive. P naught is 1 atmosphere. That is 1 times 10 to the 5th. Make sure you change it to pascals. Plus the density. This has mercury, so you have to look in your table. That's 13,600 for mercury times 10 times H. H is 0.1, excuse me, 0.1 meters. And so that gives me my, it's 113, so 1.136 times 10 to the 5th, which is just 1.1 atmospheres. I think I asked for it in pascals. 2 questions. On the one that I did. Yeah, in might have been. Yeah. Is that you said? Oh, that. It does have to be. Yeah, because it's separate. I see. For that. Can they go ahead of that? Yeah, that is. Okay. Other particular questions on these exams? You haven't looked at them yet, have you? Nobody's looked at them. Okay. Don't forget our Young's modulus stuff. I said there are a lot of loosely connected ideas, and we did this a week or more ago. That F over A is equal to the Young's modulus times delta L over L naught. And in this case, you're looking for the original length. And a lot of these are just knowing the equations and knowing what to solve for. The original length would be L naught. Make sure you know all your principles too and what they represent. This is a good listing of them. We have Bernoulli's principle, the equation of continuity, Archimedes' principle, and Pascal's principle. All four of those came up. Bernoulli's principle. This is the principle behind an aircraft wing. As the pressure goes down, let's write these things down. So if you're making flashcards, this might be useful for you if you like flashcards. So for Bernoulli, based on the conservation of energy, as the velocity goes up, the pressure goes down. What else? I think that's probably it. The continuity equation. I mean, there is the equation too, right? P1 plus 1/2 rho V1 squared plus rho GH equals a constant. For the continuity equation, this is based on the conservation of matter. As area goes up, V goes down, and our equation about this was A1 V1 equals A2 V2. The Pascal's principle says that a pressure is felt throughout an incompressible fluid. Throughout an incompressible fluid. Remember, we drew this picture of a piston, and we said that whatever pressure is here is also here and here. It has to be an incompressible fluid for that to happen. And the equation for that was just F1 over A1 equals F2 over A2. That particular equation is not on your equation sheet, by the way. This, the equation for pressure is, so I don't really consider that an equation so much as just saying that this pressure becomes this pressure. So that P1 is equal to P2. And then the other one was Archimedes' principle. That is that the buoyant force equals the weight of the displaced fluid. The equation for that was the buoyant force is equal to rho times V times G. That's density of the fluid, volume of the object, times G. So those are the four big principles, our laws that we discussed in class. Make sure you know them, sort of what they represent, what equations are connected to them, the results of them, like for Bernoulli and the continuity equation. Right? Particular questions, John? Okay, so I'm going to stop this. Make sure I get your name before you leave.